Just under 11 years before Chernobyl exploded and contaminated swathes of Eastern Europe, we turn our attention far north to the very first reactor of the Leningrad Nuclear Power Plant. On November 30th, 1975, this reactor would suffer an accident that came frighteningly close to causing its complete destruction. This is the story of the Leningrad Chernobyl, from inside the control room and inside the reactor core. To understand this accident, we will need to take a look at the difficulties surrounding the previous year of operation for Leningrad Unit 1. As was customary with all RBMKs on startup, the reactor core had about 240 channels filled with additional boron absorbers, instead of fuel, to keep it stable. As these additional absorbers were gradually removed to compensate for fuel burnup, an issue began to manifest: the positive void coefficient of reactivity. At launch, RBMKs in fact had a negative void coefficient, where the boiling of water in the channels reduced the reactivity. When the void coefficient became increasingly positive, the operators controlling the reactor could find themselves having to move control rods every 5 seconds just to keep the reactor stable. The positive void coefficient manifested in RBMKs as the fuel burned up, and the percentage of fissile uranium in the fuel rods decreased. Already, the nuclear fuel had only 1.8% uranium-235, the specific isotope that can actually sustain fission in an RBMK. For comparison, VVERs and most Western reactors had 3 to 4%. If increasing the fuel enrichment brought down the positive void coefficient and made the reactor more stable, why didn't they just do that? In fact, it would be more economic, according to calculations. And so it was decided. But before they could perform this switch to more enriched fuel, events played out that may feel familiar to those who have at least heard what happened at Chernobyl in April of 1986. Also, please note that a few eyewitnesses and reports into this accident contradict each other quite a lot. This is, in my opinion, the closest reconstruction of events that night. It is the evening of November 29th, 1975. Leningrad Unit 1 is currently at roughly 2,600 megawatts of thermal power, having been started up following scheduled maintenance, and just encountered an issue with one of the 2 turbines connected to the reactor. The solution is simple: reduce the power down to half, about 1,600 megawatts, disconnect the faulty turbine, and hold 1,600 megawatts until it is repaired, which could take days. Easy enough. A shift change occurs at midnight on November 30th. The new operators agree to continue, and by 2 AM they are at half power and ready to shut down the turbine. So, one simple job for the senior turbine control engineer: flip the switch that shuts down the generator on the turbine currently turned off. Unfortunately, he did flip the right switch, but on the wrong desk, the one for the generator connected to the still running turbine. So now the turbine connected to the reactor activates its own emergency systems in response to losing a generator and shuts down. In turn, the steam valves to the turbine also close, and this then triggers an emergency protection scram of Leningrad Unit 1, shutting it down. That unlucky SIUT has not only shut down the wrong generator, but also the wrong turbine, and now the entire reactor, taking almost 500 megawatts from the electrical grid. But the reactor is not fully shut down. It's in a phase called hot shutdown. The reactor is subcritical, yes, but the temperatures and pressures are still the same as if the reactor was still running. Xenon poisoning aside, it would be easy to just withdraw the control rods and get the power climbing. The deputy station shift supervisor sees what has happened and orders the reactor to be started up again. After some delay, the senior reactor control engineer complies and begins to withdraw the control rods. HBO's Chernobyl miniseries makes many mistakes, but one thing it explains well even though misplaced in the tale of events, is the concept of a Xenon Pit. One of the most common products of nuclear fission, tellurium-135, quickly beta decays into iodine-135, with a half-life of 6 hours, which itself beta decays into xenon-135. So, every 6 hours, half the iodine in the core will become xenon, and xenon-135 is the strongest known neutron absorber. It means that they are dealing with the xenon levels of a reactor running somewhere between 2,600 and 1,600 megawatts, and increasing, and they're at 0 megawatts. If it gets too severe, if there's too much xenon in the core, the reactor can fall into a xenon pit, where there's too much poison in the core to raise the power. It was a situation the operators could avoid though, if they were fast enough, but what they could not avoid were the other consequences of a build-up in xenon. A change in the distribution of neutrons inside the core into unpredictable shapes that the operators had no way of understanding. They would have never encountered them before. The most difficult aspect to contend with was the distribution of neutrons in the height of the core. The xenon buildup had shifted the peak number of neutrons downward in the core, but the peak concentration of neutrons radially, or horizontally, was spread out further from the centre than during normal operation. The SIUR began to raise the power, following protocol, for now anyway. The first step was always to get the reactor to the so-called minimum controllable level, a level where the power could be maintained by the automatic regulators, or automatic control rods. The value was, roughly, 160 megawatts. The problem was that the xenon poisoning had become so severe, the operator found himself withdrawing more control rods than ever before. The operating reactivity margin, the number of control rods that were inserted in the core, had once sat at 35. It quickly fell below 8, the prescribed control rod limit at this power level at the time. In order to get even this far, they had to disable the lateral ionization chambers, threatening to shut down the reactor due to the extremely abnormal radial distribution of neutrons. Still, they managed to reach a suitable power level to connect the automatic regulators and continue to raise the power towards 1600 megawatts. While raising the power out of this AR limit, the SIUR, the Senior Reactor Control Engineer, soon had his second stroke of bad luck. As soon as he raised the power above the minimum controllable level, the reactor shut down a second time. Apparently, they'd been controlling the water level in the steam separators manually, and in doing so sent a sudden flow of cold feed water to one half of the reactor. This collapsed the voids in the reactor on said half. The voids important for increasing reactivity, and so the distribution of reactivity across the reactor was completely skewed, much higher on the other side. But the supervisors were still demanding the SIUR to raise the power and reconnect the turbine. So he starts again, pulling all the control rods out the core to fight the xenon buildup. Again, the ORM falls to low levels. By 6:15 AM in the morning, 4 hours after the turbine shutdown had started this mess, the automatic control rods are again connected to the reactor, and this time they actually begin to raise the power above the minimum controllable level. At this point, the SIUR rapidly ramps up the power, from about 160 megawatts to 800 megawatts in 18 minutes. So quick, in fact, that twice they received emergency protection signals due to the speed of the power increase. Control rods insert to compensate. They are again withdrawn, to a point where approximately only 3.5 control rods are left in the reactor. They're able to turn on the turbine, connect it to the reactor, synchronize it with the grid, and begin to increase the electrical current flowing into the grid to around 300 megawatts. It's all going well. But then, something unusual happens, and the atmosphere in the control room changes from calm to confusion, as reactor power climbed by 100 megawatts in less than 30 seconds. Something bad is happening in the core, something the operators had never experienced before. The SIUR panics, as alarms began to sound about reduced coolant flow in certain channels. They had ramped up in power so rapidly that water was no longer entering the channels. It was all steam. He turns off the automatic control and begins to insert the groups of automatic control rods manually to fight the numerous reduced flow alarms. And it does work. Once all the groups of automatic control rods were inserted, the reactor was stabilized back down to 100 megawatts. Another alarm sounded: humidity in the graphite stack. A zirconium channel had ruptured, depressuring the channel, and now steam was leaking into the graphite stack. This is very bad, as it likely means the fuel channel itself has ruptured. Again, the SIUR presses the AZ5 button, and the reactor is shut down, and stays shut down. The channel that had ruptured was channel 1333, on the periphery of the reactor, and the reason as to why the accident occurred remains clouded in confusion and opinions manipulated by the Chernobyl disaster almost 11 years later. What appears to have happened is quite simple. When the reactor was restarted the first and second time, the majority of the reactor power was not primarily coming from the centre of the core, like normal. The neutron distribution had in fact shifted out from the poisoned centre. Quadrupling the power in about 15 minutes led to the neutron field spiking outwards and rapidly catching the channels in the area in a destabilizing feedback loop fueled by a positive void coefficient. The early RBMKs lacked manual control rods on the periphery of the core, and so there were already few control rods able to stop this spreading out of the neutron field. The channel ran away uncontrollably, going from 25% of full power to 75% in less than a minute, overheating and stressing the zirconium channel, causing almost a meter of it near the bottom of the core to split open at temperatures of 800 degrees Celsius. The inside of the core was a mess. Radioactive water had damaged the graphite blocks. In order to get the reactor restarted, all of the water and the graphite had to be cleaned. Water passed through filters and air through the graphite stack. But the filters were never designed for a ruptured fuel channel, nor the radioactivity it leaked. Radioactive emissions spiked at Leningrad, and then quickly fell out on the populated areas of Sosnovyy Bor, the Baltic Sea, and even all the way up to Finland. When Finnish monitors detected it, their government complained to Soviet authorities. Soviet authorities denied any accident occurring. When the radiation was purged, it was time to extract the damaged fuel rods and replace them. 32 fuel rods surrounding channel 1333 had burned out in the accident, needing to be extracted and replaced before the reactor could resume operation. 1333 was different. The fuel channel had become deformed when it ruptured, and so, when they tried to raise it using the refueling machine, it got stuck, meaning they were trapped with a now partially removed fuel rod. They went with a new plan: cut the fuel rod using a welding torch. And somehow this succeeded. However, the biological protection of the refueling machine failed to descend. This meant that workers had to instead manually assist in withdrawing the burnt fuel, using crowbars in teams of 2 working short periods to minimize their dose. This was a classic example of the ethos of the medium machine building ministry, and the Soviet nuclear industry as a whole. If your team screws up at work and causes an accident, then you eliminate the consequences, no matter the cost. Eventually, the fuel was replaced, and the reactor was restarted, resuming normal operations. After the accident, the operating logs from that night were sealed, including to those who witnessed the accident. This was just the beginning of an investigation by the organisations that ran the Leningrad Nuclear Power Plant. Sredmash, the Ministry of Medium Machine Building that oversaw nuclear development, Nikiat, and the Kachatov Institute. The actions of the operators were somewhat overlooked in the initial official reports. It was they who chose to restart the reactor in a poisoned state. They who disabled ionization chambers that were warning of the imbalance. They who restarted a second time, and they who quadrupled the reactivity in less than 20 minutes. Nor did the report focus directly on the technology involved. The size of the reactor and the uneven neutron field distribution were never considered issues. Instead, they solely placed the blame on a defective zirconium channel. It couldn't take the stress of the reactor, they said. Some changes, however, were proposed and implemented. The number of control rods around the outside of the core was increased in future reactor designs. The graphite displacers were removed from the automatic regulators. Enrichment of nuclear fuel in the core was increased to 2%, as had been encouraged before the accident. But the amount of graphite in the core, a key issue raised in the accident report, remained. The positive void coefficient remained. These issues would only receive full attention after the Chernobyl disaster once again highlighted flaws in the reactor design. In the years after the accident, some have asked why Leningrad 1 didn't share the same fate as its younger sister. Why didn't the Leningrad Chernobyl happen? Because, to anyone who had just read the 1986 report, or watched the HBO Chernobyl TV series, this must all seem familiar. It's a late night, the reactor is operating at half power, and due to operator error, its power plummets. The operators get an order to raise the power, prioritizing performance over safety. And as they do so, an inexplicable power surge occurs and AZ5 is pressed. The only difference in these scenarios is that in one case, the reactor explodes. In the other, it does not. Of course, these stories are in reality different. As those of you who have seen my How Chernobyl Exploded series, the devil lies in the details. While a notable power increase clearly prompting the use of the AZ5 button was present at Leningrad rather than at Chernobyl, multiple arguments have been set forth as to why the Leningrad incident was so much less severe. Let's take a few minutes to consider them. In the opinion of this channel, as has been laid out in the 1975 to 1986 Pre-Chernobyl history video, the key difference between Leningrad and Chernobyl lies in a virtually unknown difference between the design of the control rods. The graphite displacers of the control rods were longer in 1975 at Leningrad Unit 1 versus the graphite displacers of the control rods in 1986 at Chernobyl Unit 4. A shortening of the graphite displacers, even a seemingly minor one, occurred at a very sensitive area at the bottom of an RBMK reactor core. Shorter graphite displacers meant longer water columns that absorbed reaction-causing neutrons, which when pushed out by the displacers upon shutdown could cause an increase in reactivity. I believe that the experimental discovery of the positive scram effect, an incredible 8 years after the Leningrad accident at Chernobyl Unit 4 and Ignalina Unit 1, was not a coincidence. Those newer reactors had a number of design changes implemented in them, among them a change to the design of the control rods, the danger of which was misunderstood until after the Chernobyl disaster. In the Masters of Weaponized Narration Part 2 video, I brought up how, according to INSAG 7, the dependence of reactivity inserted upon shutdown on the number of control rods in the reactor core prior to shutdown was researched not before, but after Chernobyl. As fate would have it, a YouTube commenter claiming to have worked under Valery Legasov at the Kurchatov Institute of Atomic Energy at the time of the disaster echoes this part of INSAG 7 in recounting that upon returning to the Kurchatov Institute 5 months after the disaster, Legasov asked engineers to study this topic. Chernobyl and RBMK reactor history remains to a significant extent opaque topics. So if anyone who may have had some involvement or knows something from roughly 40 years ago, please feel free to contact this channel at the following email address. As it so happens, while I was researching for an upcoming video, I came across the following. In post-Chernobyl struggle of where to lay the blame between the powerful Ministry of Medium Machine Building, under which the Kurchatov Institute of Atomic Energy and Nikiet fell, that was responsible for nuclear weapons in the Soviet Union as well as for expertise on nuclear power plants, and the Civilian Ministry of Energy that was responsible for operating commercial nuclear power plants. The Deputy Minister of the Ministry of Energy, Gennady Shasharin, drafted a letter to Soviet leader Gorbachev. In it, we find this quote: "During the creation of the second stages of the RBMK, this drawback in the design of the CPS rods was further intensified, due to the shortening of the displacers and an increase in the number of rods. This, ladies and gentlemen, and others, is a confirmation of what we have suspected for a long time on this channel. There was a significant increase in any pre-existing positive scram effect due to a shortening of control rod graphite displacers in newer RBMK units. There is no accurate understanding of the Chernobyl disaster, of why it had not occurred earlier, without taking this central fact into consideration. We are not aware of any analysis, except for perhaps Alexander Rumyantsev's, that acknowledges this difference. This is not unexpected, as when it comes to Chernobyl, a shortening of the graphite displacers would have been an extremely sensitive bit of information for the Soviets. After all, in Shasharin's letter, it is noted that the Ministry of Medium Machine Building, Efim Slavsky, and the director of the Kurchatov Institute of Atomic Energy, Anatoly Alexandrov, the two most powerful people in the nuclear sphere in the Soviet Union, ultimately resorted to invoking the following conundrum. The basis of his arguments is as follows. Thousands of times before, the emergency protection system on RBMK reactors was activated, and they didn't explode, so it shouldn't have happened this time either. Well, we have a clear idea as to why Chernobyl was different. A particularly opinionated Leningrad operator who was present in the Unit 1 control room, Vitaly Abakumov, lists a number of differences he believed rendered Leningrad different from Chernobyl. On November 1st, 1975, at the first unit of the Leningrad Nuclear Power Plant, the initial state before the AZ-5 discharge was completely different. The first point he offers is that the Leningrad reactor was substantially fresher than the Chernobyl one. Elsewhere, he claims that the reactor physics became catastrophically bad much later, when the number of additional absorbers left was close to 10. There is, however, a funny problem with this argument. In an article by another Leningrad Unit 1 operator, who was present at the time of the accident, Abakumov decides to pick a bone with a comment he leaves in 2020. At the beginning of this comment, Abakumov notes, providing a book along with page numbers and a quote, which has also been used as a source in this video, that the number of additional absorbers at the time of the 1975 Leningrad accident was 32. Well, if we flip to page 36 of INSAG 7, what we find is that 32 additional absorbers at Leningrad Unit 1 corresponds to the same high positive void coefficient as one additional absorber at Chernobyl Unit 4. This was because the older Leningrad reactor had fuel of 1.8% enrichment. rather than the fuel of 2% enrichment. In other words, Leningrad Unit 1 and Chernobyl Unit 4 were in the same bad spot when it came to the magnitude of the positive void coefficient. Abakumov's next point concerns the coolant, or water temperature, at the core inlet. At Leningrad, he refers to it as in its normal state, far from boiling, as you might recall from Masters of Weaponized Narration Part 2, but primarily as a result of the low reactor power level. Similar thermal hydraulic parameters could occur during any power reduction of the reactor, and the reactor is operated only in boiling mode, and, according to the regulations, may be operated with minimal or even zero subcooling. See Regulations, Chapter 9. This condition is obligatory, since such operating conditions cannot be avoided in principle. They occur with any rise in power, when the pressure falls in the separators. Contrary to Abakumov's implication, and what Soviet experts attempted to argue, the coolant's temperature being close to boiling was not abnormal. It was integral to the normal conditions of an RBMK reactor. At the same time, we do not know what the temperature of the coolant was at Leningrad's core inlet. What we do know from Abakumov's description is that the technological channels were already filled with steam, which Abakumov also manages to interpret as the opposite of dangerous. Finally, we arrive yet again at the most bewildering aspect of the RBMK 1000, the operating reactivity margin, or the number of control rods in the core. Now, let's remember a few things. After an unintended short-term shutdown of the Leningrad Unit 1 reactor, something that does not appear to have occurred at Chernobyl Unit 4, following a power drop from 50% power. Remember that the Kiev delay at Chernobyl depoisoned the reactor from xenon, not poisoned it. The Leningrad operators apparently scrammed the reactor not once, but twice, successfully. We know that at some point the ORM fell to such a low value it is described as being virtually absent, somewhere in a 2 to 3.5 range of control rods in the core. Disregarding the first scram, after the unintended shutdown, Abakumov, apparently in relation to a report by the chief design engineer of the RBMK project Nikiet, who never lie, claims that the Leningrad reactor was finally shut down at an ORM of 21. Here we run into a discrepancy between the two operators who were direct participants in the incident. You see, Abakumov was not the operator who actually controlled the reactor, although he comes across like it. The operator who controlled the reactor was Senior Reactor Control Engineer MP Karask. Well, this MP Karask writes that what he did, from the point where the ORM should have been in the 2 to 3.5 range, was manually lower the automatic regulator rod groups into the reactor before scramming it with the AZ5 button. If automatic regulator rod groups lowering into the core of an RBMK 1000 reactor sounds familiar to you, that's because you watched the unanswered questions, how many control rods were in the core when AZ5 was pressed video. According to Abakumov, what Karask forgot he was doing was lowering manual control rods into the core, while the automatic ones were extracting themselves to maintain power, and then scramming the reactor. That is the 1975 Leningrad problem, ultimately. It was a very serious, although not disastrous, RBMK 1000 incident at the very first unit that was covered up from the beginning, and the details that trickle out do not have sufficiently solid form. However, that incident clearly bore similarities to the Chernobyl disaster, and suggested something was wrong with RBMK reactors from the very beginning. Its mystery survives till today. The Leningrad Unit 1 reactor shut down in 2018.